Bergmann gets them right on the first try.
Amazing.
He's been doing this a lot longer than I have.
Okay, balancing the redox reactions. We're going to learn how to balance them. You know, when we balanced reactions in the past, you just kind of guess and check. That does not work.
Negatory.
When you do a redox reaction.
Which is kind of nice, because personally, I like systematic ways of doing things. So balancing redox, you do the same thing every time. You get the right answer every time if you follow the rules.
So these are the rules. First of all, you write something called the half reactions. The half reactions, one will be the oxidation reaction, one will be the reduction reaction. You balance all the elements except H and O. You balance H's with H positive, very important. O's with H2O. You know what? This is backwards.
Kind of in the back, yeah, in reverse order.
Usually you should
yeah.
do this in the opposite order.
Yep.
And then you balance the charge with electrons. It's best to watch me do this. Multiply reactions by factors such that the electrons cancel, and then you add both half reactions. It's best to just do some examples, and so we're going to dive into examples. This assumes, by the way, that you are in an acid solution.
Yes,
right?
And if it doesn't say otherwise, you're in an acid solution.
So yeah, acid solutions are assumed here, and so now we're going to do these examples. Another thing I want to make a note of is that it's best to center everything on the page. And so I'm going to put my arrow in the center of the page, and I kind of build out from there. I'm just going to recopy this so we have a white screen. It's easier to do this. So let's start, and now I do not actually try and figure out what the charges are, or the oxidation, but I kind of see the iron is going from a 2 to a 3.
Yep.
So this is going to be one of my half reactions. I don't even bother figuring out if it's oxidation or reduction, unless the question asks me to. And so I'm going to say Fe2 positive goes to Fe3 positive. I'm going to center this on the page.
Right.
Now I need to then follow my rules. It says write the half reaction. I did that. Balance all the H's with H positive.
Well, balance all elements except H and O first.
Oh, pardon me.
So there's one iron and one iron, so that's good.
Yeah.
Balance.
Right. Well, actually, switch this over. I might switch it on your paper. Balance the O's with water. There's no O's.
No O's. Balance.
No H's.
No
H's.
H's. Yeah. But step 5 says balance charge with the electrons.
So the charge on this side is +2. The charge on this side is +3. That is not balanced. And you can only add electrons. Now, what charge do electrons have, Mr.
-1.
So if they have a negative charge, I need to make the charge go down. Which side would that be?
I'm going to put on the right side.
Yeah, on the product side. And we need how many electrons?
Just one.
Just one electron. And that is the balanced half reaction. It's being oxidized, actually.
Yes, so now the charge is +2 on both sides if we add it all up.
Yes, so then now both +2. Now let's do this next side. And then we're going to say permanganate, MnO4 negative.
Yep.
And that goes to Mn2 positive.
Yes, so this is the second half reaction.
Now balance everything except for oxygen and
Yep,
hydrogen.
so manganese, one of those and one of those, so we're good there.
We're good there. Now I need to then balance the oxygens with water.
Yep.
So I'm going to put in
4 waters on the right.
Now why 4?
Because there's 4 oxygens there on the left.
Yeah, if you have 4 oxygens, each oxygen contains 1 oxygen. Each water contains 1 oxygen, therefore you need 4 waters.
Yep.
Now we've just created a hydrogen problem.
Yes, now we have 8 hydrogens on the right, so we need 8 hydrogen ions on the left. Now you might be thinking, well, how can you just stick hydrogen ions in there? Remember, this is in an acidic environment, which means 1, it's dissolved in water, 2, there's hydrogen ions floating around.
Yeah, so there's acids involved in this.
They're just hanging out there, and then they go, hey, I think I'll be part of the reaction, so they jump right in.
All right, now we have a charge issue. Now, of course, the charges aren't balanced. This side has a charge of, let's think of this, +2 for the manganese and 0 for the water, so a total charge of +2. And this side has a charge of, now there's a +1 here, but there's 8 of them, so that's +8. And then this has a -1 charge, so that's -1, so that adds up to +7. So if you've got a +2 on one side and a 7 on the other,
we're going to need 5 electrons on the left.
5 electrons on the left. Now what we need to do is we need to add these reactions such that the electrons cancel. Now I see I have 1 electron on the left, on the right side for the iron compound, and then 5 on the other side. So what I need to do is multiply one of the reactions, or both of them, whatever it takes, to get the electrons to cancel.
Yep.
So you're looking for the lowest common multiple between 5 and 1. Well, guys, that's 5.
Yep.
So if I multiply this by 5, this number here becomes 5.
5, and 5.
This is a very easy one.
Yep.
And now I simply just add them. Notice that the electrons here are going to cancel.
Yeah.
5 electrons.
Now this is my favorite part of doing these is canceling stuff out that's on both sides of the reaction. In this case, it's just electrons. Sometimes you get all sorts of fun stuff and you get rid of it.
You want to get everything to cancel that can cancel. This one's easy in that we only have one thing to cancel. So I'm just carrying down. I brought down the 8 H positive. I brought down the permanganate. I brought down the 5 Fe2 positives, and I'll do the same thing for the other side. 5 Fe3 positive plus Mn2 positive plus 4 waters. Now you understand, folks, if this was a guess and check one, you'd be working very hard to do this over and over and over again. And let's do this K2SO4 one now. All right, so I've got K2SO4 plus NaCl makes chlorine gas plus SO3 2 minus. So what I'm going to do, now this one doesn't have like ions, I just take the K2SO4. I'm going to do this because it's going to turn into SO3. That's the change. The change actually happening, the sulfur is changing its oxidation number. So I'm going to say SO3 2 minus here. And now I need to balance, what's the rule now?
Well, first we balance the non-hydrogen, non-oxygen things. And I see 2 potassiums that need to be balanced somewhere.
There we go. I've done
Mr. Bergmann?
What?
You need a 2 in front of it to begin with.
Oh, yeah, you need 2 potassiums.
And these are potassium ions because it's in an ionic compound, so they're just going to stay ions.
Yeah, the reason I did this on purpose to make sure you understood this, folks. You can't change the charge of the potassium because the sulfur is the one changing his oxidation number charge, if you want to think of it that way.
Yep.
So I must leave everything else the same. Otherwise, you'll have 2 ups and a down, or 2 downs and an up, or something like that. All right, so we've got all the elements balanced except for oxygen. So I need to add 1 water on this side.
Yep, because you got 4 on the left and 3 on the right, so we're going to have to add 1.
And that creates a problem on the left, so I need to put 2 hydrogens on this side. And now we're going to figure out this whole charge thing. This side has a charge of +2 because of the hydrogens here. The potassium sulfate has no charge. This side has a charge of -2 + 1, -1.
0. That side's neutral.
This side has a charge of 0. So it has no charge, and so I need to add 2 electrons to this side. Okay? And this second one, I have the second half reaction. I've got the salt, the sodium chloride, going to Cl2. Now I need to balance everything. Now again, it's that sodium. I think I've learned my lesson. It's in a positive, positive charge because it is an ion.
However, look at your chlorines. You got 2 on the right and 1 on the left.
Oh yes, so I must put a 2 here.
And that's going to change the number of sodiums. There you go.
Now I have to balance my oxygens and hydrogens. But the good news on this one, of course,
there aren't any.
There aren't any O's or H's. So we can just balance the charge. The charge on this side is 0. The charge on this side is +2. So we're going to add 2 electrons to this side. We then simply add the reactions.
Hey, look at that.
Hey, and we have 2 electrons here and 2 electrons here. So they cancel. We do not have to do the lowest common multiple business. And now we just bring everything down. I don't think anything's going to cancel here.
Nope.
2 H, except the electrons, of course.
Yep, always.
Plus the potassium.
Potassium.
The potassium sulfate.
One note about that is if your electrons don't cancel for some reason, you did something wrong. So like if both of your electrons end up on the same side of the reaction, you did something wrong. You got to start all over. All right? So be careful with that.
What did I miss here?
Sulfite, potassium ions, and water.
That's this 2 minus plus 2 potassiums plus water. Now how do you know if you've gotten the reaction correct?
Well, there's a quick and easy way. Well, 2 ways. Well, you could go and count every element, make sure they're equal numbers on either side, and that's fine. You can do that. Or you can go through and just make sure the charge is the same on both sides. If the charge is the same on both sides, you probably got it right.
So this side has a charge of +2. So this charge is 0, +2, +4, -2 is +2.
Ta-da!
If you get the charges right, then you're probably very good.
Yeah, you're going to be pretty hard-pressed to get the charges right and not get everything else right.
You know, this particular problem, I think we've done enough of these examples.
Yeah, that one probably is going to show up in your homework. That is a classic redox problem.
Okay. Now, what happens if you have a basic solution? The basic solution it actually is the same exact series of steps, except for you add a step 5 and step 6 right here. These are inserted. It's the exact same steps. You're going to add hydroxides. You're going to sort of assume it's an acid solution. And once you assume it's an acid solution, you're then going to add some other things. So this should not be terribly difficult. So let me see if I can recopy this one, because I think the black screen makes it just a tad bit hard to read. So the aluminum plus the permanganate. Now this is in a basic solution.
Yep.
Where the pH should be what?
Greater than 7.
This is an interesting compound. AlOH4 negative. That's called a...
That's a complex ion or coordination compound.
You learned that in the last deal here. All right, so let's do our permanganate first.
Yep.
All right, so the permanganate is turned into, we call it manganese dioxide. So MnO4 negative turns into MnO2. So now we're going to apply our rules. So the rules that we've done before are the exact same rules. Balance everything but H's and O's.
Okay. Manganeses are okay.
We're good.
Manganeses?
Manganeses? Is that
Manganese?
Manganese.
I don't know. All
okay.
right.
So we're going to say 2 waters on this side.
Yep.
Because I need 2 extra O's.
Now we
that
do
creates
hydrogens.
an H problem, and that's 4 H's. Now, of course, but this assumes it's an acid, and we just said this is a base. You can't have H's when you have an acid. So
No.
what's the next step?
So now we go to, we have to cancel out the hydrogen ions with hydroxides.
So I'm going to add the exact same number of hydroxides to
both sides, just like algebra. What you do to one side, you do to the other.
My algebraic thing.
Yes, my algebra teacher beat that into our skulls.
That if you have 4 hydroxides mixing with 4 hydrogens, you will make
4 waters. It's a
waters.
neutralization.
So this essentially goes away right here, and this becomes 4 waters.
Yep.
But if you also make a note here, I have 4 waters here, and I have 2 waters here. What does that do?
Well, we can cancel out 2 waters from both sides.
So the 2 waters on the left side goes away, and
yep.
2 of the waters go away here, and so this now becomes 2 waters on the left side.
Yep.
Now we have everything balanced.
Mm-hmm. Except for charge.
Except for charge. So let's watch the charge here. The left side, if you add that up, there's a 0 charge here, a -1 charge here. So that's -1. 0, and then -4. So I need to add additional
3
electrons on the left side. So I'm going to say 3 electrons on the left side. This would be best if you had a wider piece of paper, and I'm running out of space.
Just as a side note, guys, if you put the electrons in before you do the hydroxide thing, you're still going to get the same answer. You can do the hydroxides first and then bounce the charge, or you can bounce the charge with the electrons and then do the hydroxides. It's going to come out in the wash.
Now, this second half